So today we'll be looking at morphometric data obtained from the Appalachian Bear Rescue. So just for a quick background, Appalachian Bear Rescue is a unique nonprofit specializing in the rehabilitation of wild black bear cubs, and their goal is to get them back to the wild as soon as possible. So they come in, injured, orphaned, what have you, and ABR does a quick turnaround and gets them right back to the wild. So whenever they come in, these bears are going to have obviously a health evaluation, among other things, but what we'll focus on today are the weight and body measurements. So, and then the morphometric data that come from that. So why is all that important? Specifically, bear treatment plans, as you can see here, having a discussion with me being curator at the Appalachian Bear Rescue. I'm discussing with the head veterinarian at the UT College of Veterinary Medicine various treatment plans for these cubs. And if we know with certainty like the ages of these cubs with any accuracy, it would definitely help us in the setting up the weaning process. When to initiate a hard wean, etc. So that's one thing that we could do from a model that could help us determine the ages of these bears. So as soon as bears are ready to go, be released back to the wild, all immobilized bears are transported to a workup area where they'll receive special markers, including lip tattoos, ear tags, pit tags, and in addition to all these bears are going to be weighed and measured prior to their release. So you can see here hind pad length, total length, chest circumference, weighing the bears. All of this is going to become very important, and these are the predictor variables that we're wanting to look at in order to determine release age. Also, future DNA analysis, we'll take hair samples for that. All these bears are going to be collared, the 2015 and 2016 bears, with GPS tracking collars, and the reason for this is so that we can hopefully track the bears, find them, and determine their survival and movements. So again, knowing release ages would really help us in using these different determining these different survival parameters. So how do we do that? Well, looking at R and using the program R here, there are two different methods that I'm going to go over today, and the first one being random forest regression analysis, and the other method is just your ordinary multiple regression analysis. So the first thing you want to do in R, obviously, is set up your working directory. You can see here I've set up mine, and then you will also need to ask R to read your table, and mine is in Excel format saved as a .csv. So we'll go ahead and do that, run that, and then just in case if you want to double check that you're in the right working directory, you can do that, and you can see we definitely are. So if you're not sure about how to execute a function, there's always the help feature, and you can see here for random forest, and also you'll want to make sure that you install the random forest package, which you can see I've already done here, and I've activated that. So, but right here, this will tell you all about in your help window classification and regression with random forest. So now it's time to begin the analysis, but you'll want to review how your variables are ordered in R first. So you can do that using the names function, and you can see here I have 21 different variables. Release age is number 21, so this is actually the response variable that I'm interested in. The random forest regression function can actually be written as below, and you'll need to determine what variable you're interested in relating to the other variables. As I said, I'm interested in this one here, the release age. And so setting up this equation, the object that I've named this object just RF1 for random forest 1. That's the name that I've assigned it. And using the function random forest, and then x equals negative 21, y data equals 21. So the reason for that, this release age being the 21st variable as listed in R under names, I want to make sure that it is not included, so hence the negative sign, in as the X variable, but I do want to make sure it's included as my Y variable. So we'll just highlight that, we'll select run, and then we'll want to view the results of the analysis. And in order to do that, you can just click on the object, select run, and as you can see here, this random forest has actually generated 500 different trees using regression, and it has tried 6 variables at each split. And you can see the listed mean of squared residuals right here, and the actual percent of variation explained was 64.33. So not bad. The next step after the random forest regression would be to determine which of these explanatory variables rank the highest in explaining the variation in your response variable. And if you want to begin by using the help feature again, that's one thing you could do. Just click right here under extract variable importance measure, and then it will give you your importance function and how you need to set that up. And you can see here it says top equals null. If you come down here to your arguments under top, you can select either a 1 or a 2, specifying the type of importance measure. So I chose 2, which is equal to the mean decrease in node impurity. That's how I chose to rank my values for this analysis. So to set up that function, just as you see here, you can simply type this importance and then your object RF1 from your random forest model, and then top equals 2, and then hit run, and it will give you a list of these node purity values, and so you can rank these. And this is actually what I used for my second paper, and you can see the table I made, variable importance values, and that's all I had to use was right there. There is a shortcut command. You can just type RF1 $importance. It's going to give you the same exact thing, just another way of going about it. As you can see here, those are the same. So that was actually pretty simple. A ton of analyses were just done in the blink of an eye, really, so it's pretty incredible how quick that works. This is actually going to be the longer part that we're going to do right now, and we are going to set up a model of explanatory variables in relation to our response variable, which is release age. And the one thing you want to start with is attaching all your data. So you can see here, looks like I've already attached it. Let's see if our names, there's all of our names again. And just before you begin with this multiple regression model, multicollinearity is always an issue with multiple regression, and so anytime you have a number of predictor variables that could be highly correlated, there's potential for concern, and in particular when you're running multiple regression. That's the good thing about the random forest regression analysis, is it not only deals with small to large sample sizes, but it also accounts for multicollinearity really well. So you can see the analysis was very quick, went very smoothly, and gave us a list of values and ranked them as far as importance values without any hiccups. So here though, let's see what's going on with the correlation between these variables, just to kind of get an idea of what we're going to run into. So I'm setting up an object, calling it C, and then I'm taking a subset of my data, which is here in this table. I'm not interested in the ID or the intake age, care days, intake weights, release weights, or weight gain in predicting release age. None of these would make sense in helping to predict release age, we're going to focus on the variables that you see through here. So in order to do that, we simply use this function here. So you put in brackets variable column 7 through 20. Again, 21's the response variable. So we do that and we click on it. Okay, that was successful. And then you'll need to install the right package. And it's actually not the car package, it's the core plot package. And once you install that, which I should already have that ready to go, and I do, it's right here, core plot, and it is ready to go. We click on it, run, and there's a number of things you could do here to change the way that this is viewed, this correlation matrix. And there's different methods. You can use squares, you can use ellipticals. What I've chose to use is numbers. So as you can see here, all the positive or the most correlation you can have is a 1, obviously, and you can see they all run down the middle because they correlate positively with themselves, each predictor variable. And the way I like the way that this correlation matrix is set up, because it's contrasted by color, so blue being positive and then the red being negative. So you can kind of, from a glance, very quickly see, what's negatively correlated versus what's positively correlated. And also there's a color gradient, so the deeper the blue, the more heavily correlated the variables are. As you can see here, chest circumference and neck circumference 0.77, or hind pad width versus neck circumference at 0.81. And then as they fade and get lighter, the association gets weaker and weaker. Same thing with the red, just a different color. So see if I can blow this up here so you can kind of see it better maybe. So I really like that right there, and it helps. But the point is that you can see all this darker navy blue, so it shows or any dark red. It's mostly darker navy blue. You can see that there is a moderate to stronger correlation between variables, and you see it quite often in this matrix here. So that tells me that we're definitely going to run into some multi-collinearity issues. So just knowing that in advance, what I've done is I have set up a model whereby there are 14 predictor variables, and what I have planned to do is just focus on the adjusted R-squared values. And as we drop terms from model 1 through model 10, just keep an eye on your adjusted R-squared and see where it goes. And the idea is to get down to 5 predictor variables that explain release age, because I'm trying to compare that with the top 5 predictor variables that were generated from the random forest regression analysis. That way I can see how these methods compare. And doing that, and importantly also, so the difference between adjusted R-squared and multiple R-squared. So right here I'll show you real quick. So if we click model 1 and click run, and then do a summary of model 1. So you can see here this is the full model, beginning with total length and going all the way down through forearm circumference. And so what I'm going to look at first is the probability of a greater value of t, and just look at the significance levels. So you can see the ones that are marked with stars versus that aren't help determine the significance value. And you can see at this point right now, total length, which was the number 1 predictor value in random forest, is actually 0.28 according to this early step of multiple regression analysis. But that could change, and that's the reason for focusing on this value here, the adjusted R-squared value, as opposed to focusing on the multiple R-squared value. You can see here the multiple R-squared value is actually almost 1. It's right at 1. So the reason for that is because as you increase the number of predictors or terms in the model, your multiple R-squared will increase. But it doesn't mean that is the best fitting model, that it explains it's able to predict the best. It could just mean essentially that, some of this large value could be attributed to noise in the model. But as the number of predictors increase, generally the number, your R squared, is going to increase. The reason I like this adjusted R squared value, and it's a lot better to go by, is because as you delete terms from the model, based on their significance values, you can keep an eye on this and see how it fluctuates. And so the adjusted R squared value is going to adjust itself based on the number of terms in the model. So it's not just, every time you increase or add another predictor term, your R squared value goes up, but it's adjusted, for each one. So it's the one you need to go by. So doing that, if you go down through here, which is what I've done, and then you select, so if you look at model 1, the first term, let's see, that's least significant, or the least significant term, which I would say is right here, front pad length. What I did is I dropped that term, and that was my model 2. And then I ran that again. So click Run, Summary, Model 2. Then go down here and look again, see if anything's changed. Whoa, now look right here at total length. It is now significant. This is what you're going to see when you deal with multicollinearity. You're going to have these issues. One, the predictor, the ability of one value to be a good predictor can be masked by another value that is highly correlated with. So that's one deal with multicollinearity. But you can see here now it has changed, and then you could look for the next one that you would want to consider omitting here. And you can see again multiple R squared value versus your adjusted R squared value. And the one that we decided to get rid of was hind pad length. So once you do that, you can move down to model 3. You just continue doing this, 4, 5, 6, and you actually reach 5 terms once you get to model 9. So you're looking at just this model right here. And then once you do that, run that, 9, run, and you can see that your multiple R squared value has dropped, as did your adjusted R squared value. But if you go on and you look, say you look at number 8 here and run it real quick, you can see that in number 8 it was 0.830 multiple R squared, but we're focusing on the adjusted R squared, which is 0.717. And if you go back to 9, or wait, if you go back to 7, run it, you can see that it was actually climbing when you went from 7 to 8. Your adjusted R squared value was climbing from 0.69, 0.693, up to 0.71 for model 7. And then once you get to, or model 8, and then once you get to model 9, it went to 0.713. So it did go down a little bit, but then if you go to model number 10 and click it, summary, you can see that it went down, it dropped a whole lot more to 0.67. So that's why I decided to stick with model 9. It just happened to be 5 variables, which is what I was shooting for, and I wanted to compare these variables to the ones that were predicted to have the highest importance values in regards to release age using the random forest regression analysis. And so using the random forest model, or using the random forest and comparing it to model 9, both models predicted total length as being a good predictor, in addition to tail length and ear length. So 3 out of 5 variables were the same between those two methods. But just to go a little further here, using this code, all this right here, I was able to rank all 10 models according to their AIC C value, so the second order AIC values, which is an adjusted AIC value for small sample size, which we're dealing with in this case. There's just not a lot to go from. And basically you start with a CAND dot models, and that's my object name, and then you want to do a list. And you can see here the double bracketing that I'm having to use, and it's just numbered on models 1 through 10, and just copy and pasting. So from right here, model 1, and pasting it to right here, and then each time I drop the term, so model 2 up here is the same as model 2. This model 2 here is the same as model 2 here, and just completing that process all the way down. So if we run this, and then you run each of these, and then you come on down and you have your mod names, because you'll need it right here for this function. So you got to create this object. So mod names, use the paste function, which most of you are probably familiar with, and then the rest of this function. So click here, run that, and then using the AIC tab function, and you want to make sure you've downloaded the right packages, and that is going to be this package right here, AIC CMODAVG. So you want to use that model selection and multi-model inference based on AIC. So once you download that, you can use this function here, AIC tab, and then we'll click that, we'll click run. Here's our table. This next, what I'm doing here next, it's all just to make it to where we have 4 digits here. And you'll see that. I'll click on it here. And there we go. So it just expands that. But basically what I've done is I've taken models 1 through 10 and ranked them according to their AIC C values. And you can see model number 1, starting with that. And you can also look at the delta AIC, or the change from model to model in the AIC C values. And you can see here, according to this analysis, that it is saying that model 10 is the best model. So we were looking at model 9, but this is actually saying that model 10 is the best. And then model 10 stacking up against the random forest regression analysis, they actually had 2 variables in common, which were total length and tail length. So 2 out of the 5 were the ones that were similar between those. So pretty close. As far as the 2 different methods, multiple regression and random forest regression analysis, I do think, however, that the random forest, firstly, it was very simple to use. Didn't take a whole lot to really start using it and understand it. But once you figure it out, it runs pretty smoothly. There probably are some drawbacks to using that method, but I do know from reading through different literature that it is very good when you have multicollinearity as an issue, in this case, which I had. So, all right, thank you.